Hello, everyone. Thank you for giving me the opportunity to talk to you, although not in person as I would have liked to. So today I want to talk about AI for science. From physics-informed machine learning to physics-informed machine intelligence is the title. Quo Vadimus in Latin means, where are we going? I'm Georges Karniadakis. I'm professor of applied mathematics at Brown University. I'm also a member of the National Academy of Engineering in the United States. I've been working on computational science and engineering for a long time, over 30 years. And in almost all cases, you encounter scenarios like the ones that I depict here in the bottom with these three buckets, where we may know all the physics about the physical phenomena that we trying to simulate, or we may know, most of the times, we know some of the physics and we have some data, and then we may have a lot of data, but very complex systems like, for example, social systems, we really don't have any governing physical laws. So what I'm going to talk about today is how we can integrate seamlessly in these physics-informed learning machines, data and physics, so we can have the best and more robust predictions for any complex physical and biomedical system. So let me explain this top picture that I have there. Here's a pattern we have on physics-informed machine learning, a concept that I introduced 7 years ago in my group. And then we're looking to the future in artificial general intelligence. And the question is, how are we prepared to incorporate this machine intelligence into physical systems? So the concept of physics-informed machine learning is very powerful because it can incorporate context, it can extract reasoning and pathways, and also elucidate very complex applications in materials, autonomy, robotics, hypersonic systems biology, and social dynamics. So our group has developed the original concepts of what is called now the scientific machine learning, the emerging scientific computing, where it includes machine learning. And I will talk about PINs, physics-informed neural networks, and neural operators, and various applications. But I will also discuss that this is an expensive computation. You may know that already, that neural networks are very expensive, like ChatGPT, very expensive to train. So here we will propose a change in this current paradigm by developing new methods inspired by the human brain that can learn nonlinear operators from multimodal inputs that can perform multitasking and also at a higher level of abstraction. So this is in a nutshell what I would like to cover today in my talk. But first, let's pose some questions. To have AI for science, in order to have technological and societal impact, we have to be able to answer questions fast and reliably that currently we cannot. So here's the first example. In non-destructive evaluation of materials, imagine you're flying an airplane and there's a little crack, like here, on the wing. Of course, you'd like that to be detected before you board the plane. And this is one of the topics that I will talk about. I was set up by the Air Force laboratory of the United States. On the biomedical side, and I've been working with Dr. Marchen, who is a neurosurgeon at Harvard Medical School for many years. And the question that he has every day when he goes to his clinic is, when do brain aneurysms for this patient will rupture so that the doctor would interfere and perform surgery before that? Right now, this is the only data they have, is a black and white imaging video. And the question is how you turn that qualitative information into quantitative information. So first before I answer these questions, I would like to briefly introduce what we call the PIN. PIN has been a disruptive technology since it was first introduced in 2017 in our group. In this paper that I have here, the citation, It's a very, very simple concept compared to other methods in computational science and engineering, all across scientific domains. And for example, here you see a standard neural network, which has 2 inputs and 2 outputs. Let's call it coordinates x1 and x2 and displacement u1, u2 in solid mechanics. Now, this is a neural network, and if we have a lot of information, lots of measurements for different locations for x1, x2, for this displacement, we can simply set up this fitting problem, this very simple mathematical expression, which is a mismatch between the predictions we make with a neural network and the data that we have collected. And by iterative methods, as I show here, basically you can determine these connections of the neural network, which are basically the weights and the bias that determine uniquely or non-uniquely this neural network, depending on the data. However, you need a lot of data, even for a very simple experiment, physical experiment, to determine this neural network. You need 10,000 or more measurements. That's extremely expensive. However, we know that in the last 3 centuries, we have built conservation laws. We have built mathematical laws for this physical phenomenon, let's say here, equilibrium in solid mechanics. And we have differential equations, partial differential equations, that I can use to first enforce the right physics. For example, you really want to have mass conservation and momentum conservation, energy conservation. So you want to enforce the right physics while at the same time, you can generate more data so that you don't have to do so many experiments. So again, the idea is, since u1 and u2 are differentiable functions, I can take derivatives and differential operators on those, and then I can form conservation laws that we know that are for this phenomenon. And of course, this can be adopted for all different applications, all scientific domains and engineering domains. And therefore, this f1 and f2 in equilibrium, I want them to be 0, and I can obtain what's called the loss function, objective function. So then instead of just the data loss function, I also have the physics loss function, and I can combine them with weights, linear weights. Let's say this is the data and this is the physics. So basically what we just did, we blended nicely and seamlessly data and physics in one statement. There are elaborate techniques already to do this, but they're expensive and they never work. This is a very simple procedure, and it's very simple because in neural networks, we have automatic ways, it's called automatic differentiation, to compute, as you can see here, all these operators, all these derivatives that are typically very expensive in computations. And then after we compute this with automatic differentiation, we can simply evaluate the physical laws by sampling the space. Here I have xy, x1, x2, but I can have time, or I can have many dimensions, and I can sample. In other words, in typical finite element simulations, one would need to build a grid. For example, fly around an airplane, an Airbus, you may need 1 month or 2 months to build a grid. Here you don't do that. You sample randomly space-time, just like you do in statistics. And by having the loss function completed, you simply minimize that to find the minimum, and that minimum is really the solution. So it's a very simple process that takes computational science from hundreds of thousands of lines of codes to only 100 lines of codes. So the joke that is, even professors now can program their own ideas. But let's go back to characterization in the problem that I mentioned on any structure. This could be, for example, an aluminum alloy. What you have in practice is a ultrasound signal, as you can see at different angles of its incidence. And from that signal, again, qualitative, you just have a video, can you extract quantitative information to find this tiny crack before it propagates for a catastrophe. So how do you do that? Well, as I said, this was a DARPA. DARPA is the agency of the Advanced Research Agency of Defense of the United States. It was a hackathon with 12 teams, and all 11 teams complained that they didn't have enough data because they were all given this video, the ultrasound video. I instruct my team to only use 10% of the data because we wanted to use the physics synergistically. We know that ultrasound propagates with a certain speed. If the medium is homogeneous, then the speed is constant. But here, of course, we have a crack. So we anticipate that the speed of sound will be non-constant. So we're trying to make it an unknown variable. So we set up the PIN, the physics-informed neural network here, which will take care of the data and also the physics. And here, this neural network will be assigned to find the speed of sound. A neural network is a functional approximator, so it makes sense to assign to this unknown speed of sound this neural network. By doing so, we simultaneously solve the two problems, having as data only the ultrasound data. And here, in a nutshell, is what we have. You see the ultrasound signal hitting this crack, let's say. This is how we write the physics, well-known physics wave propagation. And what we have here on the left is the real data. On the right, we have the simulated data using a PIN. You can see all the diffraction patterns. But most importantly, in this iterative process, we can find the contours of the function C up here on the right. And the blue contour, which corresponds to 0, is exactly the crack that we're looking for. And that's an automatic process. So basically, the neural network, we discover a new neural network, which is a function. That function is C. And that can tell us automatically that we can automate, of course, this process for production. And let's go back to the biomedical case. Now we're looking at an aneurysm. So we're really interested to see when this aneurysm will rupture at the apex or the side. And again, what we have here is visual evidence. We have qualitative information, but we can turn that qualitative information, the intensity of black and white, into a mathematical equation. And then we know that we have fluid flow. We know that it's non-Newtonian mechanics, so we can write down the equations, and we're trying to minimize the residuals. And using all this, the same PIN again, we try to do a simple minimization. By doing that, we can infer the velocity, as I show here, inside the aneurysm and the pressure. And of course, if we know the velocity and the pressure inside the 3D aneurysm, we can compute the stresses, we can compare with the yield stress, and then we can determine quantitatively and very precisely when this aneurysm will rupture. So then we have a priori information that we can pass to the neurosurgeon who can perform the operation at the right time, not prematurely. And then the last example, AI can accelerate scientific discovery. Takes years and sometimes centuries to discover a new fundamental law in physics and in engineering. So here's an example of AI Aristotle, a framework that we worked for quantitative pharmacology in a model for diabetes. It's basically a balance between insulin and glucose. These days, with wearable electronics, one can get lots of measurements on glucose, for example, monitoring glucose all the time. So we pretend that we don't have this model that people have discovered over many decades. So I zero out the right-hand sides of these equations, the main equations for insulin I, and in two different compartments. But we know the equation, let's say, for glucose, and we have data for glucose. What we want is to discover this gray box, as I call it, these yellow parts. So again, if we have the data, we turn the data into functions using neural networks. And this is what's shown here. We start from time. The phenomenon changes in time. We have an extra layer here that makes the prediction more accurate. Also, we have the PIN, as we discussed it earlier, that will take care of the data and the physics. But here, down here, we have an extra neural network, which we will assign to the unknown right-hand side, F and G. So these are the missing terms that we try to discover. If we discover this we discover the right hands of these equations. And again, following the same iterative process, minimizing the loss function as shown here, schematically, we obtain the answers. And the answers here are, we basically, from data only on the glucose, we can find data on the dynamics of the insulin. We can find 20 unknown parameters of the system of equations. And at the same time, we can find the missing physics, those terms F and G. We first can find them as neural networks, and then we can use symbolic regression. And down here, we have tables that show the two different symbolic regressors, namely PySR and GPLearn, because we want to compare that cross-verify that two different symbolic regressors give you the answer. And of course, we know the answer, but we never use the answer here in this particular example to show the concept proof of concept that we can now discover new equations just from data. It's very powerful, as you can see, in many domains, including, for example, in social dynamics today. We have lots of data using all the media like Facebook and other media, but we don't have mathematical laws that govern these interactions, these human interactions. So this is a path to the future. I don't want to go to more examples because I want to talk about also some other concepts. But here we asked ChatGPT and DALL-E to make a collection of all the areas where pins have already been used, as you can see here, from geophysics to astrophysics to mathematical finance and biomedicine, renewable energy, climate, and so on. The industry has jumped on this type of technology. In fact, Jensen Huang, the charismatic CEO of NVIDIA, picked up these methods early on in 2019. He did it the old-fashioned way. He hired one of my postdocs, the first author, Maja Raisi, behind my back, and he built a really good library that is used now for digital twins and modeling Earth, climate, and other big critical problems of our times. There are other industries that are looking at different problems using these methods. So everything looks great, but what is the problem? Well, I said already that the problem is this is not sustainable. ChatGPT requires 20 megawatts of power to retrain it. That's a lot of power. Here we show an example of the computation is required by deep learning compared to what the hardware can sustain. And this is 5-6 years ago. Now this gap between what is needed, what is required, and what we actually have available is even bigger. There's an exponential growth of the demand on deep learning computing, on GPU computing. Of course, that's made NVIDIA the biggest company in the world. You can understand from this very simple plot. But for us, the practitioners, how do we deal with it? We cannot afford, we're not Elon Musk, so we cannot afford to compute these expensive neural networks every day for critical applications in biomedicine and in engineering, in design. So we want to do something different. We want to go back to human brain, because human brain requires about 20 watts and do multitasking. All tasks that we are trying to do currently with AI can be done in a single brain. But there are certain characteristics of the human brain. There is some sort of stochasticity. There is memory very close to the processing units and so on that one can look at, as I show here on the brain. There's not just digital computing. There's part of it is digital computing, and there's also spiking. I will explain what that is. Again, we have to look at even a single human neuron to get inspiration. Here we're looking at a single human neuron. We're looking at the inputs, which are these branches or dendrites. Then we're looking at the soma or the trunk, the axon, and the synaptic output. So let's think about that, because I'm going to use this analogy with what we're trying to design. But then again, we're not looking at functions. What the human brain operates based on electric pulses, which comes as delta functions, as you can see here, which mathematically are not easy to handle. So we don't have smooth functions. We have delta functions, these electric pulses that come into the membrane of the human neuron before the human neuron fires. So here, I show on the right how one would use what is called spiking neural networks that can deal with spikes, as I show here in this schematic, to replace the current state of the art, which is continuous functions as input, using ad hoc nonlinear activation functions, to replace them with human-like activity and human-like structures, to redesign neural networks, which also have in-memory computing. And this is really the trend that is currently going on in AMD and NVIDIA and other big companies around the world who are designing neuromorphic chips. So that's the idea, to go to neuromorphic chips in the hardware and new algorithms in the software. However, we also need new mathematics. We need higher levels of abstractions. We need to be able to deal with spikes, not just continuous functions. So here is an analogy between the human neuron and a new architecture that we introduced in 2019, which we'll call neural operator. As you can see here, the two neural networks operating in sync. The one on the left has to do with the input. This is only one of the branches of the human neuron. So this is the inputs come in through this part. And then there is also another part, which is on the right. On the right, we have the output, which is the soma, we call the trunk. And those two work in sync. Notice here that unlike neural networks where the input is data, here the input is functions. In other words, we're not trying to solve one problem at a time. We're trying to solve a plurality of many problems described by functions, which could be functions space or time. The output is also functions. So we map functions to functions, not data to data. Therefore, what we represent here is what we call a mathematical operator, what we call here a neural operator. And this is called a deep operator network, which we call it DeepONet. We published this paper in Nature Machine Intelligence in 2021. Now, here's a schematic that brings together the mathematics and the neural network. So this is the mathematical expression that shows that indeed a function u can be mapped to a g of u of y, function to function, by this construction, where you can see the sigma is the activation function. This part here, the trunk, is this trunk or soma of the human neuron. This part here is one of the branches of the human neuron that is related to the human, to the input, which be this function u of x, which we sample randomly as input. So we have a function as an input and a function g of u of y as an output. So as you can see, this is very powerful because we can solve many problems all at once. These neural operators can be foundational models, can be pre-trained, and be foundational models for digital twins. Here I'm going to show you a very simple example of how can we design, using this neural operator, how we can train a neural operator to be the surrogate model for selecting metamaterials that can have certain properties, functional properties. So I'm going to talk about metamaterials, random components, light components. We put them together, and then we want them to have certain characteristics like a stress and in different directions. So here I show how we can use experiments in situ to test. So we print out, this is 3D printed materials from many very light components. These are called metamaterials, but we want them to have certain loading and unloading characteristics in terms of the stresses, energy, and so on. So here's a DeepONet. We take the random geometry as an input, then we train it for different strains, loading conditions, and so on, and we have an output. So after we train the network, we first verify that we can solve the forward problem. In other words, we can predict for unseen materials now that our students print. We don't know their properties. We can predict their properties. Then, of course, the ultimate design is, can you inverse that? Can you say, I want to have an isotropic material using these random components? The stress in every direction is the same. Can you actually design a material and then test it, print it on 3D printer and see if that's correct? And indeed, this is the case. We can predict now using a simple neural network, a very simple construct. We can predict this type of thing, as you can see here. I'm not going to give you any more details. So neural operators, as I said, can be used as foundational models for digital twins. And this DeepONet is a plurality of neural operators. Here you can replace the branch with a CNN, with a graph neural network, with a spiking neural network. And here's an example of DeepONet, which the branch is a MLP, is a standard fully connected neural network, a standard neural network, as opposed to the trunk, where one can have spikes, just like a human neuron. So one can create a plurality of architectures. And this here shows Intel computing companies, the new Loihi2, which has 1.5 billion neurons, kind of like human neurons, and it's smaller than this cup of coffee mug. So this is the future. This is what is going to happen next, because spiking neural networks require only a fraction of the energy. You require probably 1,000 times less energy that we currently spend on neural networks. We're not totally there yet, because we also need to work on different types of machine learning. Here I have a map of different types of multitask tracking, multitask learning, transfer learning, meta learning, learning to learn, so you don't have to start from scratch every time. Continual learning as information comes in is very important for digital twins and so on. For example, in transfer learning, you can learn to solve differential equations in one domain, and then with very few data, you can transfer it to different domains, so you don't need to start from scratch. This can happen for any equation. It can happen for dynamics, which limit cycles. You can transfer it to fixed points. So through transfer learning, as we have shown in this paper, again, on Nature Machine Intelligence, transfer learning is really a key idea in advancing forward computational science and engineering in every domain. Multitasking is very important. Last year, Google came and DeepMind, Demi Hassabis, who recently got the Nobel Prize in chemistry, his team came up with this architecture called Gato, the cat, that can do 600 different parts. It can solve puzzles, it can do writing and poetry and so on. So why you want to do multitasking? Because it turns out learning then is synergistic. So to learn 10 tasks is less expensive than learning 10 times one task, one at a time. So this synergy is very important. And of course, in our context for simulation science and engineering, we can learn how to solve different differential equations all at the same time, and also in different domains, and also for different loading and operating conditions. So that can be done, and then you can save, you can again speed up by a factor of 100 or more. Now, again, we can go back to nature, and we can learn, for example, from fruit flies. Question, can the fruit fly learn word embeddings? That was one of my collaborators, Dima Kroto from IBM, wrote a paper about it, because a fruit fly has a very simple brain, only 25,000 neurons, as opposed to 80 billion neurons that a human would have. So 25,000 neurons still can do multiple tasks, from smelling to assessing the humidity, flying, and so on, escaping, and so on. So then, indeed, it turns out that they can learn word embeddings, but can they learn to solve PDEs, like our graduate students and the postdocs and ourselves learn after many years of training? The answer is not quite yet, but of course we can take some inspiration, especially for the vision and how they embed images. So that was the idea behind this vision transformer, which is half of the transformer that is used in ChatGPT. It's called the vision transformer. And one of the keys about the embedding is how you take an image and you break it up into patches like stumps, and then you assign coordinates, and therefore you can keep track of and resynthesize this image. And of course, you can learn from millions of images like that all at the same time and do it in parallel. And that's why this vision transformer is very important. It's been used a lot in imaging, in autonomy and robotics. Here we wanted to use in solving PDEs, and we integrated what is called a U-net. This is the U, and we have several convolution blocks like SNNs. And then here we have the decoder, the encoder, and the decoder. And it turns out that this VITO, this integrating vision transformer with U-net architecture, called VITO for Vito Corleone, as you can see here, can do very many things, just like multitasking, as I described before. So, of course, the sky is the limit. The imagination, one can use the imagination to produce many different architectures for the future in many different domains. I'll not have any more time to go through this, and I'm sorry I'm not there to answer questions, but I just want to, finishing up here, this is my last slide, and to thank my sponsor, which is the Air Force Lab and consortium that I lead together with other good universities in the United States, Caltech and Stanford University of Utah. Thank you very much for your attention.